Thank you very much. And it is my great pleasure to introduce Professor Emma Kendrick, who is the chair of energy materials in the School of Metallurgy and Materials at the University of Birmingham. So Emma started in Birmingham in 2018 as the head of the energy materials group, following a 2 years position at the WMG at the University of Warwick, where she was a reader. Emma has moved quite a lot topic-wise as well as location-wise, and I think that's probably a key to her success. So she has a PhD from University of Kiel, a master from University of Aberdeen, and a bachelor from University of Manchester. And she was also a postdoc in Surrey. And also Emma has 10 years of industrial research experience working in new battery technologies, in particularly in the latest year of her industrial experience. She was working for Sharp Labs Europe, where she started working on sodium-ion batteries and has been leading a pioneering work in that respect. So she has overall 20 years of understanding in the science, transfer and scale up of novel functional materials into working devices, in particular batteries. And Emma's current research interests, which are very similar to mine, and we are also collaborating, and as well as Emma collaborates with a lot of other people from Imperial. So no wonder she's a popular choice for speaker in Imperial. So she does research on sustainable battery development. So Emma, please, over to you, and I look forward to your presentation.
Thanks, Magda, for that introduction. Today I thought I'd bring in some aspects of the work that I've been doing over the last few years in sustainability for batteries, and maybe just highlight a couple of things that maybe we need to think about as we're developing new battery technologies that even perhaps 10 years ago we didn't think about. And sustainability is a bit of a key word at the moment, as is circular economy. And so when we consider looking at new battery technologies or new energy storage technologies, we need to have a look at where those materials come from, what materials we're actually using, how we manufacture the materials that then go into the components, and ultimately from a battery point of view, the cell performance, cell manufacturing, and then what would happen to those materials at the end of life. And this is something that I'd like to talk to you about a little bit today in a bit of a question of sodium versus lithium. And if I get time, I'll talk about the recycling at the end. So cost and sustainability are really key for battery technologies. And if we look at the critical materials list, this is a recent report from 2020 with an updated list of materials that are strategic or critical. And what we have here is a kind of a map of these materials with the supply risk on the left-hand side here. And at the bottom, you've got economic importance. So even if there's not a particular high supply risk, for example, you can still have strategically important material, which is still on the critical material list. So an example of that is this phosphate rock here. Phosphates are used very heavily in fertilizers, and so they're of extreme economic importance and just make it into the red blobs, which are the critical raw material list for 2020. If we look at this a little bit further, we can see several materials within this section that are used for lithium-ion batteries. Now, I've highlighted the phosphate, which is used in lithium-ion phosphate. Cobalt here, which has been on the critical materials list for some time. This is of strategic importance, not just for batteries, but for stainless steel as well. And there is a supply risk for this material because of where it's geographically located. The majority of the cobalt is still mined from the Democratic Republic of Congo. And so we really need to consider how we can recycle or reclaim cobalt from end of life, whether that be steel or from batteries, to be able to reuse it in the battery space. Also here we've got natural graphite. Natural graphite is a key component for anode materials. You also see down here silicon metal. Silicon and silicon oxides are now used in the anodes as well as for PV materials and printed circuit boards. And what you just see creeping into the critical material list this year is actually lithium. So lithium is now critical due to the quantity that's used for lithium-ion batteries and other applications as well, and because of where we get it from. So there is a small supply risk at the moment. If we look at some of the other components, we have things like nickel down here, which is heavily used in batteries as well. We've got aluminium and copper, which are on the current collectors, manganese and iron, which can be used as well. These are not critical, but yet are key materials with economic importance. So if we consider the lithium versus sodium question, whether we can substitute, for example, sodium type materials for the lithium before we consider recycling. If you look at the left-hand side, we've got some very beautiful pictures here of lithium flats and lithium mining in various parts of the world. The abundance of lithium in the crust is 16 parts per million, and currently the recycling rate is less than 10%. The main producers are Australia, Chile, and China. Australia is mainly from rock, such as spodumene, and China, Bolivia, and Chile have large salt plains which you can mine the lithium from. So essentially they dissolve up the lithium chloride that's beneath the ground and bring it back up to the ground and then evaporate the water off, and you end up with these little piles of salts that can then be transformed into other materials. Interestingly, sodium is extremely abundant. I think it's the 8th most abundant material in the Earth's crust at 23,600 parts per million. It's generally not recycled because it is so abundant and quite easy to get a hold of. The main producers, again, are China is up there, US and India. And these are some pictures here. And actually, in this case, they're mined in a similar way. We can actually get salt from seawater, where we evaporate the water off and you get left with salt piles. And you can also solution mine it in a similar way, where you put water down, dissolve up the sodium chloride, pump it up, and then evaporate it to leave a similar kind of salt. This is some very pretty pictures from Spain, where they do some salt evaporation in these large kind of tank areas here. And this is some salt plains off a lake in China. So if we look at how sodium carbonate is made, which is the main material that we use for manufacturing of other types of materials, then I mentioned the solar evaporation, which is used quite heavily in Southern Europe, for example, where highly concentrated salt can be the water evaporated off and you're left with these little piles of sodium chloride. We also have rock salt, and Cheshire in the UK for many years was a big rock salt mining caverns up there in the northwest. They're actually now used for storage of documents, because it keeps away the moisture very well by having large salt mines. And you can also do the similar solution mining. And what I've done here is just given you an idea of the different types of mining that are done in Europe for sodium chloride. Now, sodium carbonate is relatively easy to make. What you do is you add some ammonium carbonate materials and calcium carbonate, and you can form calcium chloride and sodium carbonate from this. It's called the Solvay process, and this process is still used today for the production of sodium carbonate. Now, interestingly, lithium carbonate is also made in a similar way. So we can find these lithium chloride little piles which are created from evaporating off water from super concentrated lithium chloride pans. Now, this can take quite a long time, up to about 15 months. What then happens is we can actually form the lithium carbonate. The interesting thing for me when I was looking into the kind of the mining and the mineral extraction was that sodium carbonate is actually used in the manufacture of lithium carbonate, and then produces sodium chloride. So here the lithium chloride is mixed, it changes the pH, you add in the sodium carbonate and the lithium carbonate drops out of solution. On the other hand, lithium can also be mined from rock, and one of the main sources of lithium, for example, from Australia, is a rock called spodumene. This rock is first heated to form a beta spodumene, and then the lithium leached out of the rock. And again, interestingly, sodium carbonate is again used in the formation of the lithium carbonate within this system as well. And this here just gives you a little schematic of the lithium being exchanged in the process. So it's leached out of the rock to form the lithium sulfate, which then reacts with the sodium carbonate. There are other sources of lithium, and people are now looking at mining from clay, for example. And this is some other work that's done on leaching of the lithium from different rock sources. And here, more hydrothermal routes are starting to be used to extract out the lithium. Now, what I've done here is put in a lithium hydroxide production route. And this is because lithium hydroxide is quite often used as a primary source for manufacturing of materials in lithium-ion battery space. And again, interestingly, sodium carbonate is again used in the production of lithium hydroxide. In this particular route, lithium is leached again from beta spodumene, but under a hydrothermal process. It's then reacted with calcium hydroxide or lime to produce the lithium hydroxide, which is what we use for manufacturing of materials for lithium-ion cathodes in particular. So if we compare the components of the two different types of batteries, this is just an example of the battery. We have an anode, a cathode, and an electrolyte. And the anode is on a current collector, and the cathode is on a current collector. In a lithium-ion battery, the anode is on copper, typically. The anode is typically made of graphite as well, sometimes with silicon or silicon oxide in as well. And the cathode current collector is an aluminium. Now, in sodium-ion, you could use copper and aluminium, but for cost reasons and for safety reasons, aluminium can actually be used as the current collector. And this is because in lithium-ion, lithium actually intercalates into aluminium about 0.3 volts versus lithium, whereas sodium doesn't, so aluminium can be used in both. They have a similar electrolyte, which is LiPF6 in organic carbonates, or NiPF6 in organic carbonates. In terms of the anode, we've got graphite here for the lithium-ion and a hard carbon here for the sodium-ion. Both of these can be made synthetically. Graphite can also be mined. So the main difference really between these two types of battery technologies is really the cathode. And here in the lithium-ion, we use nickel, cobalt, manganese layered oxide systems or lithium-ion phosphate, whereas in the sodium-ion, cobalt is typically not utilised. Nickel, manganese and iron layered oxides are used. Or two alternative systems that are being commercialised at the moment as well is a polyanion system based on vanadium, a phosphate or phosphate fluoride, which is being developed by a company called Tiamat, and Prussian blue analogues, and Altris is looking at this in Sweden, for example, whereas Fradian in the UK is still looking at the layered oxide systems. So if we look at the cost comparisons between the two, lithium carbonate is $13,000 per metric ton, whereas sodium carbonate is quite significantly cheaper than that at $0.25 thousand per metric ton. And the main costs on the lithium-ion side are the cobalt and the nickel, whereas on the sodium side, you've got the nickel and the vanadium and a little bit of the manganese. The manganese is this cost here. This is I've got a 3 in by mistake. Okay. And so if we consider the manufacture of these materials, I'm just going to talk about the layered oxides today, which is some work that we've been doing in scaling up both the lithium high nickel layered oxide systems and also similar sodium layered oxide systems as well. These are made in quite a similar way. And what we can do is we put metal salts into solution, then we precipitate these out as a mixed hydroxide solution, precipitate that you can see here. The green here shows you that it's mainly nickel in this material. Using this methodology, you then filter and dry and then mill this material with the lithium hydroxide, and then you fire it. And by controlling your firing conditions, you can either make a pretty rubbish material or quite a good material. And although it's made in exactly the same way, it's got the same precursors in, the firing is extremely important to maintain the cation stoichiometry and limit any nickel lithium mixing within the system. And typically you can tell this from the XRD patterns by the ratio of this 003 to the 104 peaks that you see here. The bigger the ratio of this 003 to 104, the less nickel lithium mixing that you get, and you get pretty good reversible capacities up to near about 200 milliamp hours per gram of these types of material. And exactly the same is true for sodium layered materials as well. We precipitate out the mixed hydroxides. Rather than lithium hydroxide, we actually use sodium carbonate. We mill that, we fire it, and then by controlling the firing conditions and also the dopant stoichiometries, we can reduce their cycle losses, reduce hysteresis, and promote the reversibility of the system. And this XRD pattern here shows you that in this particular system, which is just a third nickel iron manganese, this is made by one of our PhD students, Tengfei, you can see that actually we need to do a little more to increase the ratio of the 003 to the 104 peak to this. And this has been improved up here with some 96% coulombic efficiency compared to the 92. Okay, so if we're considering these systems, the raw materials that we use for making sodium-ion batteries are slightly different, but we use exactly the same methods and firing temperatures and firing protocols for making the active materials. Sodium is a drop-in technology to lithium-ion, which means that all the components are manufactured in the same way with similar binders, carbon additives, and typically made by slurry cast coatings as well. And then the cells are made in the same way as lithium-ion as well, which means that if you've got similar materials which are then put into components in a similar way, into a cell in a similar way, then surely the recycling will be similar to a lithium-ion battery as well. So the main aspects that we're now considering in terms of sustainability are the materials that we've discussed coming through, but also the performance. And if we have, what we decided to look at was some of the value of the materials within the systems. And we did a quick calculation based on the metal content. And I'm just going to move to the next slide, which is a little bigger. So this graph here shows you the value of the cathode systems. And here we were considering what that value would be for recycling purposes, for example. And here I've just plotted out some standard cathode materials for lithium-ion batteries. So we've got NCA, which is nickel, cobalt, alumina. NMC, nickel, manganese, cobalt, 111 and 811. We've got lithium-ion phosphate here, lithium, manganese, oxide, spinel. And I've also compared the value of the metal components of those materials. So the blue here is lithium. We've got the purple at the top is cobalt, and the red is nickel, and a little bit of green that you see in here is manganese. I also decided to compare that to rock, spodumene. So in spodumene, you have round about 3 weight% of lithium. And interestingly, if you then look at the NCAs of the NMC, we have 7 to 8% weight of lithium in these systems. So actually, these cathode materials are really quite lithium rich compared to even the rock that we extract some of this lithium out of. So the value prospect for these cathodes for recycling purposes is actually quite high. If we look at lithium-ion phosphate, again, the lithium content of lithium-ion phosphate is quite high. It's slightly higher than the spodumene. And so there must be value for reclaiming the lithium from this material. However, the iron and the phosphate that you can see here, for example, is very low. So maybe the value for that is slightly lower. If we now look at similar sodium materials, this is a Prussian blue analog here with manganese and iron. This one has nickel and cobalt in, so it's got a higher value slightly. This is the vanadium one, and this is the nickel type material here. But you can see the value for these is significantly lower. So the question then arises, how do you improve sustainability? And going back to this little circular economy graph here, if you can't get the value from recycling purposes, which go back into raw materials, then you need to get the value from the performance. So you need to make sure, particularly for the sodium ion, that you've got long life, high performance batteries, so that the cost per lifetime or the circular economy cost overall is similar to what you get from lithium materials which have higher value. And we're still not quite sure what this means. And as sodium is such a new technology, an emerging technology in this space, there's a lot of questions that still need to be answered in terms of the sustainability. But what we've decided to focus on is optimizing the performance of these materials to try and improve that sustainability aspect for sodium-ion batteries. If we consider the strategic weighting, which is going back to the critical materials and the critical elements on that EU list, then actually some of the phosphate could increase in value because of the criticality of the phosphates for other applications, for example. Okay, so the next part of my talk, I'm going to talk more about the performance optimization of some of the electrodes that we've been developing, both for sodium-ion and lithium-ion cells. So this is some work that we've been doing on hard carbon. Hard carbon is the anode of choice for sodium-ion batteries. It has a reversible capacity of between around about 250 milliamp hours per gram, as you can see here, up to about 400, depending on the way that it's manufactured. Magda's done an awful lot of work looking at optimizing the hard carbons for sodium-ion performance. What we've been doing is trying to optimize the electrodes for performance. Now, it's quite an interesting material because you have a sloping voltage profile here and then a flat voltage profile on the bottom. And in this sloping voltage profile, it's thought that the sodiums kind of intercalate in between turbostatic layers of graphene within the hard carbon structure. And then this flat plateau here is where it's thought that we get pooling of the sodium and we get kind of metallic sodium nanoclusters forming in the vertices of where these turbostatic graphene layers interact. And there's some very nice work that was done by Melanie Britton's group at the University of Birmingham, along with Magda as well, who provided some carbons to study. And what we did was develop a cell that could go into an MRI machine and look at the chemical shift as you, in operando, as you sodiated the hard carbon. And what was really interesting here is that this is kind of the electrolyte peak. You get dissodiation happening, and this is where you get the intercalation between the turbostatic layers, and as you sodiate along the plateau, you get this plateauing out at about 500. So you get more and more quasi-metallic as you sodiate the hard carbon material. Now, one of the issues that we have in hard carbon is actually it does tend to form dendrites over time, and then we can short the cells and they don't perform quite so well. And one of the very interesting things that we saw within this with this cell is because we developed a cell which had a hard carbon and a layered oxide cathode in it, we could actually look at the specific metallic sodium as well. And these two little graphs points here at 1 and 2 actually show spectra that was captured during the sloping voltage profile bit. And what you can see is we actually got initially sodium metal plating out on the surface before, as we also got the intercalation, which then disappeared as we then went to the metallic pseudoclusters at the bottom. And this is the first time that this has actually been observed. It's been reported that it might happen from some electrochemistry data from Tarascon's group, but it's the first time that we'd actually seen during what we call the formation process, or the first cycles, this metallic sodium actually forming on the surface of the hard carbon. And this is a big risk for development of sodium-ion batteries, because we can then, it may aid dendrite growth over time. We also did some work with UCL and Julia Weaving, who also showed some really nice work which confirmed what we saw from the MRI from Raman, where we got an SEI formation at the beginning, got intercalation in the sloping voltage profile, and then this poor occupancy of these pseudometallic sodium at the bottom plateau. And as I was saying, one of the biggest issues that we have for long-term cycling in some of these hard carbon materials is this sodium plating. So this just gives you an example of a small electrode, which looks like as it was made. And this was cycled quite heavily and all this grey on the surface is actually metallic sodium, which forms extremely easily. And so what we thought we'd do is try to optimise the electrode better to try and stop some of this sodium dendrite formation on the surface. And what we know from electrodes is that we can further optimise both the electronic and the ionic conductivity, we should be able to reduce some of the extra processes that go on and improve rate capabilities and intercalation properties. So what we decided to do was to try and promote ionic diffusion within the electrodes. So we added in an ionic insulating material, zeolite, into the electrode structure. And what we thought this would do would be to keep electrolyte in the little electrolyte wells, so that electrolyte was present to be able to enter the hard carbon, and to try and promote ionic diffusion throughout the electrode itself. And this is mainly because if you go back up to this graph here, this flat plateau is actually has very, very slow diffusion properties on this flat plateau as we're creating these little nanoclusters of sodium. So we thought we'd try and help it somehow by improving the electrode properties. And to our great surprise, it actually worked. And this was some work that we were doing initially at Sharp. It's work done by Daniela Ledrock, who then did a PhD at UCL as well, to try and create or promote high power capability within our electrodes. And with all the high power work that we did, we got this plating. But by putting in an insulator, which is kind of counterintuitive, we were able to actually reduce this plating quite significantly. And so initially we thought, oh, that's very exciting. This must be because we've actually created a greater 3D network for this ionic diffusion throughout the electrode. And we did quite a lot of work looking at the specifics of the diffusion. And this is some diffusion coefficient calculations that we got from galvanic intermittent titration techniques, GITT. And you can see again here that this higher diffusion coefficient rate is the sloping voltage profile, and this very low diffusion, 2 orders of magnitude lower, happens on the plateau region, on that low plateau region. And when you cycle it as a standard electrode, the diffusion coefficient reduces quite dramatically as you cycle it, as you can see here. And we thought this was because we were blocking the pores over time, and we couldn't, an electrolyte wasn't getting to where it needed to be. If we put a small amount of this zeolite in and substituted it for the carbon black, although our overall resistance increased in our electrode, and this little white patches that you can see here are the nanozeolite that we've added. These bits here are the carbon black. We found that we could actually improve the diffusion coefficient compared to over time and compared to what we had. And whereas these low diffusion coefficients down here were still observed for the standard electrode, when a little bit of addition in, we got slightly higher diffusion coefficients on this bottom plateau. And then we looked at it in a little more detail, and this was some nice cross-sectional work done by Dominika from our group. And what she showed that actually during cycling, we blocked all the pores of our electrode from the SEI growth as we were cycling it. So essentially the SEI is not stable in this material, and all these white bits that you see in between the hard carbon is actually the interface layer that's grown between the hard carbon particles. With a zeolite additive, we still had small pores in our electrode. So yes, we'd improved the porosity over time of the electrode, but it's not from how we originally thought it was working. And we ended up doing more work this time on using it as an electrolyte additive to show that what was actually happening in here is that we were stabilizing the interface layers over time. And we did some work on some full cells looking at electrolyte additives. And this shows you here a full cell. And this is in collaboration with a project with Faradian, who provided us with the cathode materials. And you can see here, just by adding a nanozeolite additive, we actually prolonged the lifetime of a full cell quite significantly to something which had no additive in at all. We also compared it to what is normally added to a standard electrolyte for sodium ion, which is FeC. And it's thought that the fluorine content in the FeC helps to form a stable interface layer. And from some work that we did, we actually showed this to be also counter to what we actually observed. So in our pristine hard carbon, on the surface of our hard carbon after cycling, we started to see a small growth in sodium fluoride over time. As you would expect with the FeC additive, we had quite a lot of sodium fluoride on the surface, which started to decrease as you cycled it, indicating that actually this interface was still not stable over time. And then under SEM, what you can see is these little square patches which are over the surface of the hard carbon. And this is actually sodium fluoride crystallites forming on the surface of the hard carbon, whereas in the nanozeolite, you didn't get any. And what we found was that the nanozeolite was actually mopping up things like HF and water. And the water decomposition, well, the water reacts with the NaPF salt to form HF, which then forms the sodium fluoride. And by putting the zeolite in, we actually stabilized the interface by removing parasitic reactions from the electrolyte decomposition. And that's what stabilized it. So going back to what was quite a lot of work initially to try and promote high power electrodes for sodium ion, we actually found that the zeolite additive did not do what we thought, but actually stabilize the SEI layer instead. And we proved this by adding it to the electrolyte also. So the next bit that I wanted to talk about is also then moving into electrode design, but talking about some structured electrodes that we've been working on again for some time. If you look in the left-hand side here, this is a typical slurry cast coating, which is one of the first coatings that we did, which is on our reel-to-reel at Birmingham that we have. This is quite difficult to obtain thick electrodes or high coat weight electrodes for high energy. The performances are This gives you an example of one of the performances of those materials. This is a graphite material. Its theoretical capacity is 372. And from this particular thick electrode, we're aiming for about 3.3 milliamp hours per centimeter squared coating here. You can see we get quite a fast fade rate. And without an awful lot of optimization, this is what we get for the high coat weight electrodes. And this is in part because we haven't optimized the electronic conductivity and we haven't optimized the ionic conductivity or the porosity or tortuosity of our system. And so what we decided to do was look at different methods of manufacturing electrodes. And this is some work that we did as part of an Innovate UK project with KWSP and also Matthew Capener from University of Warwick. What we were doing was using a syringe dispenser to actually make patterned electrodes. So we could actually syringe out, almost like 3D print, our electrodes with very little waste in a structured design. And this is one example of a design that we had where we could create little valleys and troughs in between our electrode as we coated it, coated at the same coat weights that we had for our slurry cast coating on our reel-to-reel as well. And this is an example of this is how the slurry dispenser works. So we have to optimize our ink to be able to extrude out of this machine, and then we can print different types of designs. This particular electrode that we're printing at the moment is actually a homogeneous cast, almost like a homogeneous electrode without any ridges in it. But we could also modify the inks so that we could create different slumping effects to either create these large flat electrodes here or these more structured in design electrodes that you see at the right hand side. And so in order to do that, what we did was add in a secondary solvent into the inks to try and control the rheology better. And this miscible secondary solvent we used was a fatty alcohol. It was octanol. The red and the orange that you see here is no additive and a small amount of 0.1 weight% in water going in. As soon as we upped it to 0.5%, you can see the rheology properties changed quite significantly. This is a very similar technique to what's used for things like face creams. A secondary solvent is added to change sixoctopy and the feel of your cream as you make your cream. And so we're using a very similar method now here to change the rheological properties and the slumping to make sure that we can actually get defined deposition as we print our electrodes. And this happens by a capillary mechanism. So what happens is you put your secondary solvent in and it forms these little capillary joins between the particles, changing the sixoctopy and also your viscosity of your ink quite considerably, even with tiny amounts of additive. And this was really important to make sure that we could actually extrude and print the ink through the little nozzles that you saw on that syringe. What we also found is that it had a huge effect on the microstructure of our electrodes. So what you can see here at the top is a microstructure of our graphite electrodes, graphite flake electrodes with no addition. The dispersion of the carbon black wasn't as optimized as we might have liked. And the other thing that we noted is that this is a 3D, so this is a cross-sectional picture of our electrodes after they were printed and then dried. And you can see here also that most of our graphite is kind of lying perpendicular to the current collector, which is at the bottom. And we could analyze what kind of angle our graphite was lying at from doing some digital analysis of these images. And this graph here just gives you an idea of whether it's lying flat or perpendicular. And if we look at the no additive here, you can see that the majority is less than 30 degrees in direction. So it's kind of like lying this way here. And as we added more secondary solvent in, we can actually change the microstructure and the alignment of the graphite flakes. And in this 1% here, you can see that we've got different pore sizes. We've got a slightly different distribution of our carbon black, and you can see that our graphite flakes are no longer just lying flat or perpendicular to the current collector. We put a 10 weight% in, and although we got quite a big change, you can see here in your microstructure, you actually got a collapse in a way of your microstructure, and you started to get agglomerates of your systems instead of nice dispersion with good porosity. So huge porosity and then not so big porosity. But we did have more less alignment of oscillates in this system. And these are just some of the graphs to show you how we could optimize some of these electrode properties. Okay. So finally, one of the things I wanted to mention was that we can now analyze these electrode properties for some of their parameters. And we're looking at not only cycle life, which we can improve here, as you can see from the printed electrodes, but also we can look at the diffusion properties and some of the kinetics and the current exchange densities, which we can extract from some of the EIS data. And this data is quite important because we can use that in optimizing our performance properties of our electrodes. And this is something that we're also using for input into multi-physics models along with Imperial as well. So we're providing some of those parameters to go into those multi-physics models. So here we just summarize that electrode. We can modify the tortuosity and the properties by changing the additives that go into the electrode, and also by changing the structures of the electrode to optimize transport properties of electrons and ions. And the big thing to notice here is just our tortuosity is very low in the printed electrodes because we've got some gaps that our electrolyte can go through to be able to then get to the electrodes. Okay, so just in summary, sustainability is just more than just materials. It's about how you make the materials, manufacturing, and also the performance. And from what we've noted, actually, it's a performance that we probably need to work on most for some of the sodium-ion work, because it's not yet clear whether we can recycle sodium-ion batteries, because the value of the components is so much lower than it is for equivalent in lithium-ion. And so by optimizing the performance properties by looking at structured electrodes or additives and understanding the structure performance correlations, we can extract out the fundamentals of the thermodynamics and the kinetics, or the electronic and ion transport properties, which guides not only the manufacturing, but can also be used in multi-physics models to understand and predict cell life as well, or cell performance. And just like to thank the group. This is a recent group picture that you can see at the top, and some group pictures in less COVID times. And the other thing I'd just like to highlight is that we talk about sustainability a lot. The group has actually got together to implement this in the lab as well. And they got awarded silver award this year for Green Impact Labs. So this is sustainability in work practices within the labs, actually doing the work for sustainable batteries, led by Scott Gordon, who's one of our research fellows. And thank you very much for your attention.
Thank you. Thank you, Emma. That was a brilliant talk. I very much enjoyed it. I like how you went from sustainability, raw materials, to cathodes, anodes, electrolytes, interface, and then electrodes and manufacturing. So that was great. So I'm going to read some questions from the audience. So the first question is from Kunal, and he asks, how do you ensure uniform electrode thicknesses when depositing the slurry through the syringe?
I see, that's interesting. We don't get uniform electrode thicknesses. What we're actually trying to do, I wonder if I can go back, is to optimize channels within the electrode to try and promote electrolyte transport, particularly for high power. But in this case, actually, what it promoted was cycle life rather than power. And that's because I don't think the density of the electrodes was high enough, which meant we didn't have good enough electron transport throughout the layers. Now, I think it's interesting because we can form structured electrodes like this, and we can get improved performance properties in a half cell using a lithium metal counter electrode. But when we come to use it in a full cell, for example, then I think that's a really quite interesting question. Where does the lithium go? What is the current density at different points? And do we end up then having a mismatch between our anode and cathode because of this effect? So I think that's a really good kind of question and something that we haven't quite got around to answering yet.
Thank you. I don't see more questions, so please, if you do have questions, put them in the Q&A section for Emma. Oh, here, there's another one from James. Do you think that similar optimization of structure could be applicable to other anode materials for sodium-ion batteries, such as alloys?
Yeah, I think again, that's another interesting question. Yes, this is something that we would really like to do, and we're trying to convince Magda to make us some tin carbon composites at the moment so that we can start testing them. And I think actually that could be really important for the longevity, because you get such a big volume expansion with things like tin for sodium-ion batteries, that volume expansion needs to go somewhere. And you also still need to maintain a flux of sodium ions to the surface to get your sodium into your material and back out again. So your engineering, your electrode, I think, has to be very clever. It has to be able to cope with the constant expansion and contraction of your materials and still maintain mechanical integrity and electrochemical integrity. So it could be a really interesting thing to look at.
Great. Another question is, how do you make sure that the zeolite, I think they means coated or the electrode surface, probably.
Okay, so we had a couple of things with that. We didn't coat it on the surface. We actually mixed it into our electrode. So we actually dispersed it throughout our electrode, thinking we'd form really nice ionic transport networks, similar to how you would from electronic transport networks. However, it ended up not being the case. It's just that it had a different effect, which was to mop up all the HF and water that was produced in the cell. And then we proved that by just adding it into an electrolyte, where it did the same thing as what it did in the electrode.
So following on the zeolite, Milo is asking if the proposed mechanism of the zeolite addition is that it acts as an in situ water scavenger, avoiding unwanted hydrolysis reaction over time. And then he further asks, does this mean that the benefit has a finite lifetime until the zeolite is saturated?
Yeah, I think it probably does matter. Again, just because this as well, I mean, degradation happens, you can't stop it. And you can see, we did actually XPS, Mark Walker here at University of Warwick is a bit of an XPS guru, and he helped us enormously with this work. And it wasn't just the sodium fluoride that we saw that was changing in terms of the makeup of the SEI layer. It was also some of the organics on the surface. And essentially, we saw that by adding in the nanozeolite, we definitely had a greater stability of the interface layers, in that the peaks didn't change that much over time compared to what you saw with non in the FEC. But you can see here we're starting to get some sodium fluoride formation again here. So it does look like we've kind of mopped up bits and pieces, but it does have a finite lifetime. So the trick is to not get water in it at the first place, and that's actually quite difficult to do.
Great. I see no more. Oh no, there's one more question on what I was about to ask one, but I guess I'll have to ask from the audience first. With the 1-octanol, what was the difference in the orientation of the graphite flakes measured after calendaring?
Okay, So, calendaring. So yes, so we didn't calendar it, and I can tell you why we didn't. Well, we did calendar some and we didn't calendar some of the others. What we were looking at was to see if we could change the morphology and the alignment by adding this secondary solvent, and we could. The problem with calendaring is that it, as I think this is what Jack is alluding to, you kind of you squash it and things align back together again. So we still have to find some way of being able to improve the electronic conductivity, whether that's through calendaring or through another method, and reducing the porosity to get it to be a working electrode. I think this was very much kind of a proof of principle to show that we could change the microstructure by using different secondary solvents and quantities of secondary solvents. But there's still a way to go, I think, before we understand it well enough for it to be a production style electrode. Because without a doubt, we have porosities in this of round about 50–60%, which is far too high. It needs to be down to 25–30% for a graphite electrode, really. And the calendaring kind of destroys the microstructure, and it doesn't make such a nice kind of picture. So yes, we'd still need to find some ways of improving that. Okay.
And maybe one last question, because we kind of need to finish. So we have 1 minute. You have to answer very quickly, Emma. From Harry says, it is not more than just cost of material that drives how recycled they are. For example, paper is cheap and gets lots recycled. I guess it's dependent on the cost of recycling versus cost of materials.
Yeah, but it's also on the ability to deconstruct and reclaim the material. So yes, absolutely. Cost is just one of the things, and we've also been doing quite a lot of work on recycling to look at improving the cost. So we have a shredder, and you can see the shredded material that's coming out the shredder there. It's kind of, we then have to separate that out to create purer materials waste streams that then need reprocessing as well. And one of the other things we've been looking at is disassembly of that. So whether that would create purer materials waste streams that are more easily processed compared to the shredding. And again, I don't have an answer for you. It's still work in progress, but I think at the moment, what we're finding is the shredded materials take quite a lot to purify. There's compared to what we do from a disassembly process. But from a disassembly process, it's quite difficult to automate the disassembly because everything is a different shape, different size, got tabs in different positions and module sizes. Nothing is built to a standard. So nothing is designed for disassembly or designed for taking apart. And there's still quite a lot to do there.
Great. Okay, I think we will need to stop here because it's 5 o'clock. And this again, thank you very much, Emma, for being our last speaker of the year in the IMSE seminar series, distinguished seminar series. And thank you all. And I guess we'll see you all next year, hopefully soon under better circumstances.